At high power, the entire core behaved predictably as a single system. But at low power, the neutron flux could tilt, effectively splitting the core into independent, unstable zones. One pocket of the reactor could experience a rapid increase in fission, while another remained quiet. This extreme spatial instability meant that the core became highly sensitive to even the smallest localized reactivity changes. In this forbidden low-power region, the physics of the machine became chaotic, completely eroding the reactor's inherent safety margins. The operators were no longer driving a stable, self-regulating machine. They had entered a realm where the reactor's physical design provided no defensive cushion, leaving them highly vulnerable to any sudden, localized shift in power. The physical construction of the RBMK 1000's control rods contained a hidden vulnerability that would only reveal itself under these low-power conditions. To control the nuclear chain reaction, the reactor relied on 211 control rods. The primary function of these rods was to absorb neutrons and slow down fission. For this reason, the main body of each rod was made of boron carbide, a highly effective neutron absorber. But the way these rods were assembled introduced a dangerous complication. Because the reactor core was exceptionally tall, designers wanted to make sure that when a control rod was fully withdrawn, water did not fill the empty channel and absorb too many neutrons. To prevent this, engineers attached a 5-meter-long graphite block, known as a displacer, to the bottom of each boron carbide rod. Under normal operations, this setup worked well. When a rod was fully withdrawn, the graphite displacer sat directly inside the core, replacing water and helping to keep the reactor running efficiently. But this meant that when the emergency shutdown button, known as AZ5, was pressed, the rods had to travel a long distance downward. As the rods began their descent, the graphite displacers entered the lower part of the core first, before the boron carbide absorbers could reach the fuel. For the first 1 to 2 seconds of insertion, this graphite displaced the water at the bottom of the channels. Since graphite is an excellent moderator and water is a mild absorber, this movement temporarily increased the rate of fission in the lower core. During standard high-power operation, this brief spike in reactivity lasted only a moment and was harmless. But in an unstable, xenon-poisoned reactor operating far below safe limits, this design characteristic would behave very differently. At 1:03, the crew shut down the automatic emergency core cooling system. They closed the isolation valves to prevent a sudden flood of cold water from thermal shocking the reactor, which they feared would disrupt the turbine rundown measurements. While standard for this specific test protocol, this decision turned off the plant's primary safety net. Next, operators bypassed the automatic shutdown triggers linked to the steam valves and turbine status, switching the automatic regulator to manual control. This meant the reactor would no longer scram on its own if the turbines stopped spinning. The operators wanted to prevent premature trips from interrupting their window of observation, but their actions dismantled the passive defenses of the RBMK. By disabling these automatic safety loops, the crew removed the active safeguards that could have overridden manual control. They were now operating a highly temperamental machine without its automatic emergency brakes, relying entirely on manual instruments and human reflexes to detect a runaway reaction before it was too late. Behind these choices lay a rigid decision-making environment. Deputy Chief Engineer Anatoly Dyatlov operated under intense institutional pressure to complete this long-delayed test. In the Soviet industrial system, failing to deliver results or delaying schedules carried severe professional consequences. This administrative environment prioritized production over safety, leading Dyatlov to repeatedly order the night crew to continue even as the reactor resisted their efforts. The operators themselves lacked the engineering knowledge to recognize the danger. Their training had not prepared them for low-power operations, and they had no access to simulation tools to model the core's erratic behavior. Specific physical realities remained hidden from them. The Soviet scientific establishment had never informed its reactor operators about the positive void coefficient or the graphite tip scram effect. The crew believed they were managing a stubborn, underpowered machine. They did not know that their training, their documentation, and the culture of secrecy had left them entirely defenseless.